Hello and welcome to Lab 4 on oscillations. The goals for this lab are to compare the predicted motion and the observed motion of the mass, which is hung by a string in both the x and y directions using a video given to us in which we find data by the tracker, and then a model which we are going to make ourselves. And we will plot the energy changes in kinetic energy, gravitational potential, and spring potential in the change in total energy. Key formulas we'll be using is Newton's second law, kinetic gravitational potential and spring potential energies, and then knowing that the net energy change should be zero. Some constants, the mass of the ball is given us, and it was 0.402, and then the starting x and y position are given in the ball position vector, and our velocity is 0 to start. More known constants, gravity 9.8 meters per second downward, our spring constant, which was found using 4 pi squared times the mass over the oscillation period, which we found using our data in the tracker app. And then our L naught, which is found using the force of gravity is equal to the force of spring. Then we find the length of the ball for every iteration, which is the position of the ball minus the spring position, which is the standard start of the spring. L hat, which is the length of L over the magnitude for each position of the vector, and then S, which is the x value we will use in our spring force every single time, which is the magnitude of the length minus initial relax length. And then we plug in all of our standard kinetic, gravitational, and spring energy formulas, and then the total energy is the sum of all. Here we use we define our initial energies for every run, where we make the previous energy value our initial for this run. Our gravitational vector is mg in the y direction. Our spring force is negative kx, in this case, k subscript s times s, which is the x value here, and then times L hat to give our directions. Our F net is the sum of both of these. Our ball vector is using Newton's second law, and it is simply the velocity plus the F net divided by its mass times the change in time. And then the ball position is updated every run with the velocity times time. Our energy formulas, we plug in these same formulas, and then we find the changes using delta K, where we take our new minus our initial, which we found earlier, and then we get the delta E, the change in total energy, by adding them all together. And show it. Here you can see the spring move from right to left. This is a change in energy versus time graph. You can see that in the middle we have the change in total energy, which is a constant 0, and the others are all oscillating. We have our model versus experiment. We're very close to being accurate for both x and y position. And as you can see, until the very end, the change in total energy remains to be 0, which goes to our first question. Is the energy principle satisfied? And yes, the energy principle is satisfied, as there is a total net change in energy being constantly 0, which means that there's no external energy being added. Another question, what are the differences in the oscillation periods for x and y axis, and why is this? And for this, I used our data from the tracker app, where we found our ball's position. And for the x-axis, we had 4.83 seconds for 3 oscillations, which gave us a 1.61 second period. The y-axis of 4.558 second for 3 oscillations, which gives us 5.12 second period. And this difference comes from a loss of energy in the y direction from the effect of gravity and the spring constantly moving, while in the x direction, there is no force acting on it other than the spring force, which constantly moves. Thank you.